So firstly, we'll be discussing what is the basic difference between HTTP and HTTPS. Then we'll be leading forward towards the how HTTPS basically secures your data and how TLS Handshake is implemented in HTTP and how certificates are, uh, transferred to each other and how browser actually verifies whether the certificate is authentic or not. So the basic difference between HTTP and HTTPS is that HTTP is used to request and receive data over the World Wide Web, and it works on the port 80. Data is sent in plain text, meaning anyone intercepting the traffic, like on public Wi-Fi, can read or modify it. So think of HTTP like sending a postcard. Anyone who handles it, the mailman, sorting center, etc., can read your message and even change it before it reaches the receiver. So in HTTPS, which is Hypertext Transfer Protocol Secure. So the secure basically adds the security in it, and it's basically HTTP with security added. We use encryption, which is TLS, to protect data in transit and server authentication to ensure you're talking to the genuine website, genuine server. So initially, there was SSL, but now we use TLS, Transport Layer Security, which is a more advanced and secure protocol. It works on the port 443 and usually shown with the padlock symbol in the browser or address bar. So think of it as like sending your message inside a sealed envelope that only the intended receiver can open. Even if someone intercepts it, they'll just see encrypted gibberish, plus you also check the receiver's ID certificate before trusting them. So this is the basic difference between HTTP and HTTPS. So let's move how this HTTPS works. So in HTTP, we have basically only these two parts like TCP handshake and then data transmission. This part 2 and 3 becomes part of TLS handshake, and it is only in HTTP, and it is basically providing the embedded security in it. So, firstly, we'll discuss each out of them. So let's go for the TCP handshake. So let's start with the very first step, the TCP handshake. Before HTTPS or encryption even begins, the client and the server must first create a basic connection using TCP. So it's a simple three-way process. So client sends the TCP sync, basically saying, "Hey, are you there?" So and server replies with the sync ACK, like saying, "Yes, I'm here. I hear you." So finally, the client sends an acknowledged message, meaning that, cool, we are connected. So now the line between them is open, but still in plain text. So there is no encryption yet. So if this were HTTP, anyone sitting on the same Wi-Fi or a network could sniff these packets. So because no encryption is yet implemented, so there might be a man in the middle. Uh, Possible there, which who can easily intercept and read your packets. Then session hijacking, TCP spoofing, anything can happen at this stage. So now to protect this communication and to transform HTTP to HTTPS, we do this certificate exchange and verification. Once the TCP is ready, so HTTPS initiates the TLS handshake. So this is basically a part of the TLS handshake. So it starts with the client hello message. The server browser says, uh, this is basically the browser, and this is the server. So the browser says, "Hey server, I support these encryption methods, and this is my random value." In this hello, he is basically telling all this. I support these um, encryption methods, TLS variants. So in the next few slides, we'll be discussing about that what all are the TLS variants. Previously, it used to be SSL, then there was the TLS 1, 1.2, 1.3. So nowadays we use 1.2 and 1.3. In previous versions, there were some security flow issues. So so once the client or once the browser gives the server the list TLS variants it has and the random value. So the server replies with the server hello. He is basically saying that, all right, let's use this cipher suit, and here's my random value too, and this is the latest TLS variant which I support and you also support. Let's fix on this. So they basically decide the mutual things on which they'll be communicating, on which they'll be, going ahead. It's a pact sort of a thing. So then the server sends a digital certificate. It's basically an ID card issued by a trusted certificate authority. So, and the certificate contains this server's public key, its domain name, and CA digital signature. So it's a complete process that how that that server of that website gets that certificate, from where it will get that certificate, how the certificate will prove the authenticity of the server, and how basically this browser will understand whether through this certificate that this website is an authentic website or not. So this is how the certificate is generated. We have a separate video for that. I'll be uploading it in 2 or 3 days. You must be checking in my description. I'll be providing the link to this certificate generation, because it's a whole new topic. So we'll be discussing in another video. So let's take to the certificate check here. So the browser client checks the CA's signature. It verifies that the certificate was actually issued by a trusted authority, not a fake one. If the certificate is valid and the domain name matches, the client trusts the server and continues. You can think of this as like visiting a bank. Someone behind the counter says, "Hi, I'm a manager." But you don't just take their words for it. You ask for their official ID. If it's the government issued verified, you know you are safe to share your information. So possible attacks will be fake certificate. So somebody could send a fake certificate, compromise certificate authority, DNS spoofing or phishing. But whatsoever the case is, so if it's a fake, or if there is some sort of an issue going on with that certificate authority or certificates, you must be receiving a, a, um, a warning sign. So we have, I have included it. There are 5 to 6 uh, parts where we actually uh, discuss that how these warning signs come. If the certificate is expired, if the domain mismatches, if it's an incorrect certificate chain, it's basically how the browser checks its trusted root trusted certificates, and then to the intermediate, and then the website certificate. This is a complete chain. It basically opens up each certificate to get a public IP of another certificate. So it's we'll be discussing this certificate chain, trusted certificate chain, in another video, which I've already discussed. So then there's a self-signed certificate that one cannot sign its own certificate unless it's a root certificate. So if that's the case, you get the warning. Then if there's a mixed content, you also get the warning. So moving ahead. So this step is crucial. It ensures you're talking to a real server, not an impersonator. So now step 3 is a key exchange, creating a shared secret key. So now that the client trusts the server, both sides need to create a shared secret key for encryption. So what has happened so far? Firstly, they have acknowledged that they can communicate with each other through the TCP handshake. Number two, they now the browser knows that the server I'm communicating to is actually the real server. So now in third step, they have to save their, now they have trust. They have no trust issues between each other, but they are afraid of some man in the middle or some attacker who can actually read their communication. So now they will exchange keys to tackle that. So the client generates a random value called a pre-master key, and then encrypts it using the server's public key from the certificate. So that browser, once the certificate which is sent to the browser, once it's verified, it will get the public key. So it then it basically encrypts that key which it has to send to the server with that public key from the certificate, and then send it to the server. Now server decrypts it with its private key, and both sides now have the same pre-master key. Using that plus the random values exchanged earlier, both sides generate the same session key. In certificate exchange, we discussed that they have shared some random values. So finally, both send change cipherspecs managing, saying that like from now on we'll be talking on this encrypted form. So you can imagine just like two people are crowded in the room, and the client writes a secret number on a note, locks it in a box using the server's public key, and send it across the room. Only the server has the key, the private key, to open it. Now both knows the secret, their session key, and we can talk privately even if others are listening. So there's still a possibility of man in the middle, uh, but this fails because only the real servers can decrypt the messages with its private key. You will only get the garbage values if you are the man in the middle. You can perform downgraded attacks where an attacker tries to force both sides to use weak cipher source so they can later decrypt traffic more easily. Then you can perform replay attacks at this stage even. So in step 4, you basically do data transmission. Now that both sides have shared the same session key, they finally start encrypted communication. From this point, all HTTP requests and responses are encrypted using the symmetric encryption. So the same key on both sides. So when you type your password, send a payment info, or load a web page, the data is converted into a ciphertext before it leaves your device, and only the server can decrypt it. You can think of it as like two people are now using a secret language only they understand. Even if someone's sitting right next to them, they'll just hear a gibberish. So possible solutions or possible attacks at this stage will be traffic analysis, compromised session key, mixed content warnings. So this step is where actual HTTPS data transfer happens, completely private, fast, and encrypted. So as we discussed that in the certificate exchange, they basically come to the point that what TLS variants the browser has and what TLS variants the server has. So they basically come to a consensus that what TLS variant they'll be using. So I have a small, description what the difference between, you know, the two major TLS variants which we use. One is TLS 1.2 and one is 1.3. So basic difference is that in TLS 1.2 we have more steps. It's a bit slower process because there's a hello. Initially they just communicate, then they share their key exchange, change cipher specs. They tell each other that okay, now from now on we'll be I am ready for the changing my cipher position. Then it also communicate the same back. Then but in TLS 1.3, we have reduced these steps. We in the first hello, we share this key. So the entire handshake process become faster and more secure. Instead of multiple round trips, the client now includes its key share in the first message. So it's like saying hello and handling over your half of the secret key at the same time. The server replies with its key share certificate, completes the handshake almost instantly. Both sides now compute the session key right away and start encrypting communication after just one round trip. It's like two people who have met before and already know how to exchange secrets quickly. They greet, verify, and start talking privately almost immediately. So it's basically security improvements are old weak algorithm like RSA key exchange and SHA are gone. Forward secrecy is mandatory here. It also prevents downgrade attacks, replay, certificate manipulation. In 1.3, it gives us both speed and security, which is why modern browsers and sites use it by default. So after the uh, so this is each step explained in detail. You can check it out if you want to. But the basic thing is, okay, we can discuss some scenarios here. So if client supports TLS 1.2 and server supports TLS 1.2 and 3, so which TLS will be selected by the server? It will be 1.2 because if server chooses 1.3 and client does not have, it would be it would be an error. Then the second scenario is if the client supports 1.2 and the server supports 1.3 only, then what happened if the handshake will fail because they do not have the same TLS version. And third scenario is if the client support 1.3 and the server supports TLS 1.2, again it's not possible because the server does not support it. So the basic rule is that the handshake uses the highest TLS version supported by both client and server. So client will give a list of the TLS versions it has, and server will actually select that TLS version from the top, which it also has. So this is, if there is no common version, the handshake will fail.